Hi, I am Molly Danielsson. I am director of Recode. Recode is a nonprofit based out of Portland, Oregon. We work to ensure legal access for innovative solutions for buildings. We have worked for the last 5 years, particularly around water and sanitation issues. In 2008, we worked to legalize greywater reuse in Oregon. And over the last 3 years, we worked on 2 different composting toilet codes. And I'm going to tell you a bit today about just a real brief about codes and the particular nuances of sanitation codes and what technology neutral codes are like and how those can be useful, what Recode is doing, and then what you in Vermont can do. So just to back up, most of America's water and sanitation infrastructure were developed based on an assumption of abundant water. Virtually unlimited water to pipe in and virtually unlimited ability to pipe water out somewhere else where you could treat it or dilute it into a really large body of water. Yet that assumption of abundant water we now know is wrong. In California, there's a drought and a crisis around water going on there. And even in more wet places like Western Oregon, our waste of water has real consequences. We spend millions of dollars every year building bigger pipes to contain the amount of wastewater we're making instead of fashioning a more efficient system. So there are some pretty great solutions to this that work within our current infrastructure. So greywater is one solution. So many engineers and builders have been working on ways to safely reuse water from sinks, showers, and washing machines. This is what we call greywater. It's clean enough for some purposes, like watering the landscape. And there's also been a lot of innovations around in sanitation as well. For example, composting toilets use no water and create a safe byproduct that can be reused. So there are some alternatives, but there are barriers to reusing water, and that is how Recode got started. We got started in 2008. There was an environmental sustainability center that wanted to showcase green practices, and they realized that it was illegal to do a greywater installation, and they could either work to create an exemption for their site, or they could work to create exemptions to create a permitting process for everyone in Oregon. And that is what they did. And that is what we have kind of been working on ever since, is how to create really mainstream legal access pathways for everyone. So I'm gonna take you through my slideshow now. And this is developed for Oregon, but I think this is really relevant to what you're doing in Vermont. So first of all, the problem with sanitation, of course, is we care about poop and pee. And poop is really the high disease risk we're concerned about, right? It's really high in nutrients, lots of organic matter, but it's also high in pathogens, and we don't want those pathogens to come in contact with our mouth. So this diagram is just why we are trying to prevent it coming in contact with our fingers, because our fingers might touch our mouth at some point, and then we will ingest them and we will get sick. So urine, on the other hand, is really low disease risk, but it's high in nutrients. So nutrients in the right place are a fertilizer, and nutrients in the wrong place are a pollutant. So that's why we really care about where we're putting all this poop and pee, and that we're treating it safely for the pathogens. So with pee, it's not a concern about treatment, right? Because it's usually sterile when it comes out of the body, unless someone has a blood contamination issue, maybe a kidney infection. So unless under those circumstances, it's fairly low disease risk. But there are some other things in our urine that we should think about, which are pharmaceuticals and hormones. So urine is our bodies trying to clean out our bloodstream. So the kidneys are working to pull out pharmaceuticals and hormones from our bloodstream and then release any salts or whatever byproducts into our pee, and that's how we get them out of our system. So I'm going to do a super, super rough history of sanitation here that I hope will help kind of ground the context of what you're talking about, because anytime you want to talk about changing the system, I think it's important to think about how we kind of got here. Yeah. In 1854, there was another cholera outbreak in London, and these have been happening every so often. At the time, people believed that the bad smells in the street were what was getting people sick. There were open cesspits of poop and pee and animal manure all over the cities, and people thought that if they could just remove that smell, they would stop getting sick. And Dr. Snow worked hard to prove to people that it wasn't the smells. It was pathogens in the poop and pee that were contaminating the water and spreading disease. We now call these germs. So this is the emergence of germ theory. So these were things that people couldn't see at the time except for with a microscope. So it was hard to convince people that it was real because they couldn't see the threat. And we're humans. We tend to only believe things we can see. So it's difficult. So he was able to show people that when one well got polluted because there was a leaky cesspit next door, that if that cesspit contained feces contaminated with cholera, that when that poop leaked into that water, whoever tapped that well and drank from it got sick. So this spurred authorities to adopt more or less germ theory, and they implemented sewers and septic systems as a response to this. Both the idea that both in a response to the idea that bad smells carry disease. So the sewers actually enclosed the poop and took it away from people to get rid of the smells, and it also kept our water from being contaminated by the incoming sewage. So it really addressed both issues at the same time. So they built these sewers in London and they flushed the sewage downstream into rivers and lakes. This response helped deal with pathogens in the city, but we didn't solve the problem for downstream communities until much later. So let's fast track a little bit till 1950s in the US. In the 1948, the US passed a law requiring that sewer systems go to treatment plants. So sewer systems had been built, but they weren't always going to wastewater treatment plants, where they were then required to bleach the material before returning it to lakes and waters. And this act also provided for funding for wastewater treatment plants. So if you go to a wastewater treatment plant in the US, it's probably built in the 1950s, and that's because this funding was available then. The next big influence on sanitation came from concern about the degraded quality of our waterways. So in the 60s and 70s, lakes and streams across the US were beginning to look pretty bad. All the nutrients in the sewage were making waterways toxic. So even though the pathogens have been killed, there's still a lot of nutrients that are causing different issues. So in my graph here, this is kind of the, oh no, the environment matters area. So in 1972, we banned treatment plants from polluting lakes and rivers. So treatment plants added an additional level of treatment called secondary treatment. So let's back up to the 50s. They started instituting primary treatment. Primary treatment you can think of like a French press coffee filter. So you add your coffee grounds and you add the water. So all the sewage and everything is mixed together. And what a primary treatment does is it physically separates the coffee grounds or the heavy organic materials to the bottom to clarify it. So it's a physical process of removing the solids, just like the French press is a physical process of pushing down the grounds. So by the 70s, it's required that we have more than just this French press approach, actually having biological treatment. And I don't have a very good coffee metaphor for this. So secondary treatment is going to reduce the amount of organic material in there, and it's actually going to introduce usually aerobic systems, so they'll actually bubble water in to keep soil bacteria alive underwater. Really hard to come up with a good metaphor for this one. In the 90s, further environmental awareness led to the banning of ocean dumping. So in the 70s, we were taking all the sewage sludge that comes to the bottom, and we're dumping it in the oceans because it was no longer allowed to go to the rivers and lakes. And in the 90s, we banned that ocean dumping of that the rich solids at the bottom. And the EPA created guidelines for land applying that sewage sludge, which involved testing and partially removing heavy metals and other pollutants that we were aware of at the time before that material was applied to the land. And today, over half of our sewage sludge is applied to the land. So that's a very rough history of what has happened in cities. And in rural areas, there hasn't been quite as many innovations and changes. And a lot of that, I think, has to do with the codes. So people started installing septic systems around the same time as the sewers. And the idea was really, it's getting things away underground underneath us so that we won't be contacting our feces. So codes around these septic systems weren't put in place until about 100 years later. And they were based on some incorrect assumptions, which have left a legacy on the on-site or septic system codes that we have today. And when I say on-site, it's just a generic term for any treatment system that is used on-site location to treat a household waste. So it's households that don't or can't connect to a sewer. So number one, these codes assume that if we have one prescribed design, this is going to be useful for all sites. And the idea was that these prescriptive codes would allow for anyone to follow the rules. Second was the idea that compliance with public health goals would meet environmental protection goals, which we now know is not true. The idea was if people weren't getting sick, then the environment must not be getting sick either. And the third one is that septic systems were going to be temporary and eventually everyone would sewer up. We now know that sewers are incredibly costly and even in medium dense cities don't always make financial sense. So in the 70s, as a growing response to environmental concerns in areas where septic systems weren't working, people started doing a variety of different systems. In Oregon, we call these alternative treatment technologies. So these are water-based systems like septic tanks that create cleaner output but still require the solids to be pumped out for further treatment. And we'll talk more about that later. So alternative treatment technologies vary, and I can show you a few, from wood chip filter systems to having some small bubblers to having some kind of materials for bacteria to grow on to increase treatment. So as a result of our concern for the environment and germs, we now require every building to have a wastewater treatment system to manage our pee and our poop. But what we call a wastewater treatment system right now is restricted because it doesn't include systems like composting toilets and greywater as part of a wastewater treatment system. So let's look at the amount that we're talking about. What are we actually trying to treat? We're trying to treat people's poop and pee and their other outputs like greywater. So these two barrels represent the amount of urine and the amount of poop per person that someone makes. And here's another graphic of that with my friend Lucian for scale. So the quantity is probably a lot smaller than you imagine. What makes it really large is that we use a lot of water to flush it. And the amount of water pictured here is used by the latest dual flush toilet in 1 year. So this would be much larger if this were, say, a 5-gallon or a 3-gallon flush toilet. So right now, the only options that meet a building's requirement to have wastewater treatment is a sewer or a septic system or a septic-like system, like an alternative treatment technology. And those have some pretty high costs associated with them. Here is a graphic of how we regulate the reuse of water, like rainwater and greywater, composting toilets, and anything related to the toilet here in Oregon. And this infographic can be found at recodenow.org. So we regulate everything that is inside the house is within the building department. Anything that leaves the house, like the black water coming out of these pipes, is regulated by either on-site or by the sewer system, and those fall under the federal EPA 503 rules. And the gray water coming out of the house here on the left is regulated by the Department of Environmental Quality in the case of Oregon. I'm not sure how you guys are looking to do it, but that is our approach. And currently, composting toilets have a tricky situation because even though they are right now within the plumbing department. So Recode wrote the REACH code, which is in the bottom right corner. I can point to the screen, but I don't think you can see my pointing's not very useful in this case. And we require the material, like the humus, to be put under 6 inches of soil. The new IATMO code requires compost to be put on top of the soil, which is the most active biological zone, and then have 3 inches of carbon material like wood chips put on top of it. So that's much safer because it will be incorporated into the soil much faster instead of being put deep down where it's pretty cold and there's not likely to have a lot of activity going on. So it's actually much safer to have it be put on top of the soil and then just covered with wood chips. So you can spend more time with this. I shared this more as just a reference if you want to know how we do things in Oregon and how that works. So just really briefly, the benefits to a wastewater treatment plant, right? There's no effort for users. It manages the whole city's waste. It's a large-scale process for returning nutrients to the soil. But the downside is it wasn't designed to return nutrients to the soil, right? Back in the 1850s when they started implementing sewers, and then in the 1950s when they started implementing wastewater treatment plants, the idea was really about dealing with pathogens. And it's not designed to remove persistent pollutants like pharmaceuticals before that land application. So here are pictures of our wastewater treatment plant in Portland, which is above average, doing really great. And this whole process of wastewater treatment uses 5% of Origin's energy. And in Portland, we have about 4 overflows per year. Another downside is this is all water-based, so it really requires the use of water no matter what. So let's talk about a septic tank, which is really fun because a lot of people don't know how a septic system works. So the big innovation with the septic system is this T-joint here on the left corner. So that T assures that fats are not going to be able to rise up and clog the pipe. And it allows liquid or coffee to kind of come in, and the solids or coffee grounds settle to the bottom. And most of the heavy metals and organics will tend to settle to the bottom with that because that's just how things bind together. Everyone loves carbon, so it binds with the carbon, which is what makes things organic. And so those settle to the bottom. So if you imagine the wastewater treatment plant primary treatment was more like a French press, a septic system is more like cowboy coffee. You pour the water in with the grounds and you're literally just waiting for the solids to settle. And then the fats rise to the top. And then once things have settled, the liquid will move into the second chamber, or in Europe it's common to have 3 chambers to allow for more settling. And that's how you get it. So you still get a little, cowboy coffee. You still get a little bit of grounds in every sip, but it's just about the amount of time is what increases the solids settling because it just has more time to settle out. So the benefits are this is low maintenance. So these solids at the bottom, they can be pumped out every 2 to 3 years. It depends on the system and the size. And it's fairly affordable. It really depends on who you have install it. So the downsides about septic systems is this wasn't designed to remove nitrogen. And when you hear nitrogen in this presentation, think pee, because that's really what we're talking about here when it comes to a household. There's not a lot of fertilizer being poured in. The fertilizer is our pee. So this nitrogen, or pee, is going right through the septic system and infiltrating through the soil. And a lot of the deep soil where this is going through isn't designed to absorb the nitrogen. It may absorb a lot of the phosphorus, cling to the rocks, but not so much the nitrogen. And these effluent plumes go down and they tend to stay towards the surface. Groundwater is slow. There's not a lot of bubbling or mixing. So when something enters the groundwater, it kind of stays on top and just flows in that direction. Effluent plumes can be detected up to 2/3 of a mile away. How do we detect this, you're probably wondering? Caffeine. You can always tell where people are, usually by testing for caffeine. So since effluent plume usually stays on the top, that's why we tend to put wells deep down, so that as the well is sucking in water, it's not accidentally sucking in the effluent plume, and because we don't want people to accidentally be ingesting other people's pee because of the things we talked about earlier, like pharmaceuticals and hormones that can be in our pee. So the other downside is, the sludge requires further treatment. The sludge is separated, but it's not treated. It still needs to be treated to remove pathogens before being applied to the land. And of course, this is also a water-based system. So what we used to think about groundwater and what we think about it now has changed as we know more about groundwater hydrology. So we used to think that septic tank plumes were kind of like paint in a paint bucket, and it would just spread out evenly. So the figure on the top shows what we thought about why setbacks were useful, because if you had these certain setbacks, no one would be polluting each other if they met the setbacks, because the material will disperse laterally. And it turns out that's not how it works. So the bottom illustration is a more accurate description of how septic tank plumes work. They actually go in a direction and they cross property boundaries. So alternatives exist that achieve higher levels of treatment than septic systems, but they tend to cost a lot more than septic systems. So up top, this is a Nitrex filter. So that's basically a bunch of really large wood chips that absorb much of the nitrogen. And then on the bottom, we have the Arenco Advantex, which is a great system. But these systems require some electricity and a little bit more maintenance. And, electricity can fail. But overall, they're good systems and they are available. But what Recode is really interested is in the systems that achieve a really high level of treatment but don't cost very much. So in between this kind of septic system ATT divide. In 2008, Recode worked on greywater, as I mentioned. And in 2012, we brought in composting toilet rules in Oregon by working on the REACH code. And in 2014, we wrote a voluntary national composting toilet code with IATMO. So we worked with IATMO to create a code. And IATMO is a model code writing organization. So this is what they do. They write the Uniform Plumbing Code. And our composting toilet is in the green supplement to the Uniform Plumbing Code, and that comes out this year. So right now the situation is septic systems and alternative treatment technologies meet a household's requirement for wastewater treatment if they don't have sewer as an option. But composting toilets and greywater reuse and urine diversion aren't considered wastewater treatment, so it doesn't help, say, a household looking for to repair a failing septic system. None of these three systems on the left can help them meet their requirement to get back up to legal. So why is this? A big thing I think is the codes. We have prescriptive codes here in Oregon for how our on-site system works, or nothing's ever purely prescriptive, but it's mostly prescriptive. So this is my metaphor I like to use for describing what prescriptive codes are. Imagine if you had a set of codes that was written, say, 70 years ago about how chairs would be legally made. So it might say, like, it has to be wooden, it has to have 4 legs measuring yay high. Whereas this wouldn't really allow for your favorite office chair today. So what Recode is working on is performance-based codes. So instead of saying what a chair has to look like, it would say a chair is anything that comfortably seats a human being. And then it would probably have like a test for what defines comfort. And that would be how you would get a lot of innovation. So we're working on having basically a range of systems be able to meet a household's need to have a wastewater treatment system. My notes here. And we've been working on this since 2012 with the DQ. So I'm going to go through some of the requirements for a performance-based code. So first you need to set a goal. How clean do we want things to be before they enter the environment? So for a performance-based code, this would say, what's your nitrogen reduction? What's your phosphorus reduction? How much are you reducing pathogens by? Is it durable, watertight, things like that? Whereas prescriptive code would just say, what are the dimensions? What are the materials? Check, check, check. You need to decide what the nutrient output is per year. So this does vary in country to country, but deciding this will help determine. So if you have a set amount that you expect an average adult to make every year in terms of poo and pee, then you can say if a household is on average 5 people, you can estimate how much pollution you expect to be created by one household and how to size a system appropriately. And third, you set design characteristics, not a specific design. So rodent proof, testable, watertight. These are the kind of characteristics you can require instead of saying exactly what it looks like. We're really interested in humble code that is future resilient. Fourth, you need a verification method. So how do you know it passed? Fifth, all this data needs to be publicly accessible. Trust, but verify. Great question, Mr. Fish. I think that these kind of codes will allow us to work with us as we learn more. So we're going to learn more about what else is dangerous. Right now, we know that nitrogen is a problem, but in the future, we might feel that pharmaceuticals are worth testing for. And these kind of codes can grow as we learn more. Another reason is these codes can use more real-world testing. Lab tests don't always predict real-world performance. For example, this could be a really expensive alternative treatment technology, but bleach would kill all the microbial life in that system, and it could pollute that afternoon because of this addition of bleach. I think it's really important that we don't specify how systems look, because this could prevent us from having innovations in the future that we might really, really like. So that's what Recode has been doing, and this is the kind of future we're trying to create. And let me tell you more about what is specific to Vermont. So I think there are many options for states like Vermont. In order to allow greywater reuse, you can adopt the best practices of the rules from the 4 states that have already legalized greywater. To allow for a range of composting toilet systems that work to protect human health, you can adopt the Uniform Plumbing Code's Green Supplement composting toilet section that Recode worked on. And that code is all ready to go. IATMO has created a code that already works within the plumbing system, and it's been vetted by their whole team of experts. If Vermont is interested in joining Oregon and creating performance-based codes to allow for a range of innovative sanitation solutions to be used instead of septic systems, like I mentioned earlier, you can partner with Recode and the Oregon Department of Environmental Quality as we work to create a model performance-based on-site code. So that's one option. In preparation for creating this model code, Recode will be traveling to Sweden and Finland this August with Abe Nohays of the Rich Earth Institute to learn more about their approach to regulating alternatives to septic systems. We'll be gathering best practices and creating educational materials needed to answer our questions and for the Department of Environmental Quality in Oregon about this approach. So you guys do have a lot of options out there, and please let us know how we can support you. Thank you so much for your time.